2.3, polynomial functions and their graphs. So this is kind of an overview of all polynomials and how we can interpret them, different things about them. So this is kind of an overview. Your polynomial function of degree n, we want to put those in standard form so that the highest power is on front and they go down when we write them. And then whatever the highest power is, that is your degree. And that degree tells us different things. The leading coefficient is the number in front of that leading term. So it's important as we do this that we know that they're in order, because that's going to signal a lot of different things to us, and that values things about that leading coefficient. If it opens up and down, it starts where, and all that good stuff. All right. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. And we go from there. So first, let's look at equations and determine if they're polynomials, and then we'll look at graphs and see if they are polynomials. So the first one here is this a polynomial? So I have 6x to the 7th plus pi x to the 5th plus 2/3 x. Now, I agree with you totally that that is an ugly equation. But the question is, are all of your variables have a whole number power? And that's what is important to know. Do they have a whole number power? They do. There's the numbers in front of them. Sure, pi is kind of ugly, but it's simply a coefficient. So yeah, it's still a polynomial. So yes, this one is a polynomial. Okay, now the question next is, what is its degree? So is it in standard form? And it is, because I have the 7th power, then the 5th power, then the 1st power, so it's in standard form. And because the highest power is 7, that is its degree, 7. Okay? For number 2, is this a polynomial? I'm seeing fractions, things like this, but don't be afraid to rewrite this as h of x equals 1/3 x squared plus 7/3, right? That's another way I can split that up. So do my variables have whole number powers? Yes. And the coefficients, or the leading coefficients, again, those really don't matter. The constant there at the end, it's all about the power. And so this is, yes, it's a polynomial. And this time it's degree, and I have it there in standard form because the x squared comes first, and then the constant is going to be 2 because that is the largest power there. All right, on 3, is this a polynomial? I have f of x equals x to the 1/3 minus 4x squared plus 7. Is that a polynomial? No. Okay, this is not a polynomial. And the reason it's not is we see that 1/3. And 1/3 is not a whole number, and you have to have a whole number to be able to do that, okay? All right, moving on to the graphs. So I don't want to go too far because I want to make sure I keep this note right there. Up here we said polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So is number 4 a polynomial? And I would say not a polynomial, and the reason is it's not smooth, okay? And if you remember, that's an absolute value function, and that's not a polynomial. The next one, is that a polynomial in step 5? And I would agree, not a polynomial. And the reason is my graph is not continuous, right? There's breaks in it. It has different curves on the same thing, so not continuous. All right, on 6 here, is this a polynomial? Everything's kind of curved, nothing takes a break, it's all one continuous line, as much as a line is, yeah. So I would say yes, that's a polynomial. Whoa, don't know what I just did there. All right, so quick identification, because if we don't have a polynomial, the rest of the rules we go through doesn't matter. We need to be with polynomials. So we're looking for things with where you can read the degree, where you can see what the power is and what kind of graph they have. Okay, so page 2. All right, leading coefficient test. Okay, so one thing that's important is, one, we have to have a polynomial. We want to put them in highest to lowest degree, and whatever is the highest degree could have something in front of it. So that number, that value in front of it is the leading coefficient. Okay, that leading coefficient is going to tell us kind of, if you just step back and think about your parabolas that we just did, if it was positive, it opened upwards. If you remember that, if it was negative, it opened downwards, right? So that is not special to your parabolas. This is true on all polynomials. So you have this leading coefficient test, okay? So one thing is we have odd degrees, okay? So things of odd degree or even degree are the two categories that these fall into, okay? So if you think of some odd degrees, okay, like y equals x, right? That's to the first power. That's 1 degree. You have this line that goes up, right? If you have y equals x to the third, right, then you start getting that little bump, but it still goes up, okay? When you think about this, both of these functions, they both started down at the bottom and they rose to the top, okay? That's what it is. So if your leading coefficient is positive, they're going to start here down at the bottom, the left side is going down, and the right side is going up every time, okay? So if you throw a negative in front of there on that leading coefficient, it's going to flip-flop it, okay? So notice here, it's going to start up at the top, and it's going to fall to the bottom. So it flip-flops that, okay? That's what that leading coefficient will do that. And that's when my leading coefficient is negative, it does that to it, okay? So as we get more and more higher powers, all it does is it adds more bumps in there. So if you look at it, this one was just the line. Then we have 2 bumps for the third. So when we get to x to the 5th, what we do is we have an extra bump in there, okay? We just kind of go another time. But every time, your end behavior is opposite on your odd ones, okay? Now when we go to our evens, if you think about it, that's my x squared up here, right? Y equals x squared, we already did. When I do like y equals x to the 4th, okay, we get this kind of W type of thing, okay? It has 2 bumps, right? Or 2 lower ones, and then it has the one in the middle or something. So every time I add 2 more to it, I just add another bump on there, okay? That's kind of what I'm doing. But the thing with our even powers is our end behavior is matching. So when our leading coefficient is positive, both of them go up to the top. If my leading coefficient is negative, both of them turn down to the bottom, okay? So without even seeing a graph, we can know some general end behaviors because of the way just the degree of the function and the leading coefficient gives us that much, okay? So if we just look at number 7 and 8 here, let me see if I can move my page. All right, on 7 and 8, I'm looking for my leading coefficient test, and I'm trying to figure out what's happening. So first things first, make sure it's in standard form. I have x to the 4th, then x squared, then x, then 3, so I'm good. So because I have degree 4, I know that I will have both of them the same because it's an even, so both of them will be the same. Because my leading coefficient is positive, I know they're both going to go up. Okay, so just a quick sketch, I'm probably doing something like this. Okay, that's what it's doing. So what I want to do here is I give it says give the end behavior. Okay, so my end behavior is up on the left, up on the right. This is my answer for my end behavior. Okay, so for number 8 with g of x, this is an odd function. I look at this, I have degree 3. So it's odd, which means it's going to go opposite. And my leading coefficient is negative, which means usually I start like this, right? But this time, because it's this, I'm going to start up and go down, so it flips the pattern, right? So my end behaviors are on the left, it's going up, on the right, it's going down. Okay, so that's my answer there for my degree 3. All right, so one piece of our lesson, just knowing which way is it going to start and which way is it going to end, okay? All right, zeros of a polynomial function. Okay, one of the things with zeros is just understanding what a zero actually is, okay? Here's some things I want you to know too. Synonyms. Zeros are also called roots, are also called solutions. Maybe one of the best ways, how about the X-Intercept, okay? Because truly that's what we're going to see the most right now is if you think about it, whenever it's time to solve a quadratic, I run through my little 5 things, right? You can graph the function, see where it crosses the x-axis. You can complete the square, take the square root, do the quadratic formula or factor. Which one would you like? if you listen carefully, when I always say that, I always say graph the function and see where it crosses the x-axis, because that is a solution, okay? So when you see these, it's asking to find the zeros or the roots or the solutions, the x-intercepts, it's asking you to solve basically, and they're all these things, okay? So there are chances that a polynomial function has no real roots or answers if it never crosses it. The only function I shouldn't say the only function, even functions are the only thing that can happen there too. Because if you think of the end behavior on an odd function, when one's going down and one's going up, it has to cross the x-axis at some point. But there's the possibility with the even functions that they never cross the x-axis. So even functions could maybe not have a solution, a real solution, but odd functions should always have at least one real solution, okay? So then we come to what we call these multiplicity things, okay? So it says if r is a zero of even multiplicity, then the graph touches the x-axis and turns around at r. If r is a zero of odd multiplicity, then the graph turns the x-axis at r, or crosses the x-axis at r. Regardless of whether the multiplicity of a zero is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. That made perfect sense to you, right? Just in your language, what you're used to. My guess is no. Okay, so here's the deal. We find these roots, okay? Now, we are used to, when we solve a quadratic, let's say we get x equals 3, x equals 7, right? So it would cross with those two. But do you remember when sometimes we factor and we get like x minus 3 times x minus 3? Right? So that means that my answer is actually x equals 3 twice. Right? Because if you think about it, a quadratic has to have two answers, but sometimes it's the same answer twice, okay? If that's the case, what's happening is your graph is coming down and it's touching, and I'm not going to be able to do this right here, it's touching right there at 3, okay? That's what's happening, but it didn't cross in, okay? So this is the deal right here. When you have even multiplicity, so this root is showing up 2 times, that's an even number, even multiplicity, then what's happening is your graph touches and turns. Okay, so this graph touched and turned at the 3 because there were 2 of them, okay? When you have something like x equals 3 and 7, this graph, you have, and I'm not going to fit it on here very well, so you have 3, you have 7, and don't ask me why I did a negative there, something like this, and your graph went through both of them, okay? So this time your x of 3 was once, and this time your x of 7 was once. So if you have an odd multiplicity, okay, so this is even multiplicity. If I have odd multiplicity, what happens is I'm going through that point and I cross across here, okay? So I have to go through once, okay? There's a good chance you're still lost right now, okay? I understand that right now. So if it shows up odd times, okay, then you're going to cross over. All right, so let's look at some examples and see if that makes more sense. So let's turn the page, right? Okay. So it says, find the zeros for each polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. Okay, number 9 is nice because it's all been factored for us, okay? So I'm just going to go ahead and make a little chart. I'm going to list my zero. I'm going to list its multiplicity, how many times it is the zero. Multiplicity. I'd be smart if I just abbreviated. And then the behavior at the graph. On the graph. How about on the graph? Okay, so first things first. What is this 0 right here? What would make that factor equal 0? Okay, 0. How many times is that a factor? Because it's just x, not x to the 5th power, x to the 7th power, it's just x. That's a multiplicity of 1. It has 1 power. It shows up as the root once. So that means my behavior on the graph, I'm going to cross. Okay, I'm going to cross the x-axis. And I'm going to be honest, if you just want to write cross, I'm fine with that. You don't have to put the x-axis. All right, I go to the next one. What would make this parenthesis equal 0? Well, that would be a value of 8. How many times is that the root? Well, because it's squared, that means it's the root 2 times. Because it's the root 2 times and 2 is even, that means when I get to 8 on the graph, I'm going to touch and turn. Okay, and it looks like I have one more here. What would make that parenthesis equal 0? Well, negative 1/3. And how many times does it appear? The multiplicity is 3. And that means I'm going to cross on the x-axis. Okay, now let me give you maybe a quick visual of what's going on here, okay? I'm going to use some of my rules from earlier, and I'm going to see if I can do some kind of a quick sketch. Okay, I know right now that I have roots at 0, at 8, so 8's down here. Oh, negative 1/3 is going to be like right there, and 8's going to be way down here. I am not to scale, and to be honest, I'm okay with that. Okay, what degree is this function? Well, if you look, this is a 3, this is a 2, this is a 1. 3 plus 2 plus 1 is 6, so it's degree 6, okay? I say that so that I can think about where my graph, my end behavior is. Oh my goodness, I do not know what I just did. Okay, so it is degree 6. Some days I think I should just stop and not do this. Okay, it doesn't like me right now. That's all I can figure out, degree 6. Okay, which means it's even, which means both end behaviors are the same. Because I see a negative leading coefficient, that means I'm going to start down, okay? It means both of I'm going to start down and I'm going to end down, okay? So here's my 3 roots. That means I'm going to do start down, I'm going to go up through that first root. I'm going to do something up here, I don't know what. When I get to 0, I'm going to cross through. And I do something over here. When I get up to here to 8, I'm going to turn and go back down, okay? Because at 8, it said touch and turn. So I touch and turn at 8, okay? I don't cross over. And I get this graph, and there's some behaviors in the middle. I don't know how high or low those bumps are in the middle, but that's the general idea of what's happening here because of knowing the zeros and their multiplicity, okay? So let's go ahead and try this next one. Notice they were not nice to me. They just gave me a great big one here. So we're going to have to figure this one out. Let's do some factoring by grouping. Maybe I have 4 terms. So I'm going to pull an x squared out, and I'm left with x plus 7. Over here, I'm going to pull out a negative 4, and I'm left with x plus 7. So that gives me an x plus 7, and it leaves me an x squared minus 4, which is going to factor again to x plus 2 and x minus 2. All right, does that factor anymore? Nope, that looks like that's all. So there's my function now in factored form. So I can see that I have roots, zeros, x-intercepts, whatever you want to call it, and behavior. Okay, so one of my zeros is negative 7. It only showed up one time because that's just to the first power, which means it's going to cross at that one. One of my zeros is negative 2. It only shows up one time, which means it will cross. My last 0 is 2. It only shows up one time, which means it'll cross. Okay, so if we think back to the original function, it was degree 3. Okay, so degree 3 here, which means my end behavior, and it was positive leading coefficient, which means it's going to start down and it's going to end up, right? That's what my leading coefficient tells me is going to happen. All right, so I have negative 7 and negative 2. I'm going to just estimate there, and then I have 2. So I'm going to start down, I'm going to cross, I'm going to come back, I'm going to cross, I'm going to come back, I'm going to cross, and I look something like that, okay? So every one of them crosses through, so I don't have to turn around at all. All right, intermediate value theorem for polynomial functions. To be honest, I don't know how many times we use this or not, but what this can tell us is, should I be able to find a root somewhere between here, okay? So the intermediate value theorem says that if you run two values through your function, and one gives you a positive answer, and one gives you a negative answer, somewhere between those two numbers, you had to cross the x-axis. Okay, so if you think about it, if you get one y that's a positive and one y that's a negative, somewhere between there, you had to cross over. And when you cross over that x-axis, that is a root, or that is a 0, or that is an answer, okay? So that's what this is doing. So I have this function, and I'm told that if I plug in the 0, I get a value. So 0 cubed minus 4 times 0 squared plus 2. Well, 0 minus 0 plus 2 will give me 2. When I plug in 1, because that's what I'm checking between 0 and 1, I get 1 cubed minus 4 times 1 squared plus 2. That's 1 minus, 1 squared is 1 times 4 is 4. 1 minus 4 is negative 3 plus 2 is negative 1. Because I have a positive and I have a negative, that means somewhere in between there is a root. Now, we know it's not 0 because we didn't get a 0. We know it's not 1 because we didn't get a 0. So it's some decimal possibly in between those two. Well, it has to be because between 0 and 1 there's only decimals. Okay. I should think before I speak. All right, next one. Here's my function again. Now I'm checking between 2 and 3 to see if there's a root, does it cross? So I plug in my 2. 3 times 2 cubed minus 8 times 2 squared plus 2 plus 2. 2 cubed is 8 times 3 is 24. 2 squared is 4 times negative 8 is negative 32. That's plus 4 at the end. 24 minus 32 is negative 8 plus 4 is negative 4. So I get a negative 4. Now let's check the 3. 3 times 3 cubed minus 8 times 3 squared plus 3 plus 2. 3 cubed is 27 times 3 is 81. 3 squared is 9 times 8 is 72, and that's a minus there. 3 plus 2 is 5. So 81 minus 72 is 9, plus 5 is 14. I have a negative, I have a positive, so somewhere in between there, there is a root because I crossed over that x-axis somewhere. So it's some decimal between 2 and 3. I should be able to find a root. All right, last page. Maybe the most complicated. This is saying, can I do these sketches? So those two sketches I just did on the other page, kind of, I'm going to lead you to kind of do it as well, okay? So first we're going to make sure our functions are in standard form or that highest to lowest power. We're going to use the leading coefficient test to determine the end behavior because that gives us a hint where and how we should start, okay? We're going to find any x-intercepts by setting f of x equal to 0, or if you think about that, the y is 0, so we're just solving them as best we can. Factoring is our friend. Remember that, factoring is our friend. If there's... if k, blah, 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 blah. What am I looking for right here? We're going to do, basically what this is saying is we're going to look and see if we can find the multiplicity chart, okay? We're going to find the y-intercept by plugging 0 in for x. That's step 3. Step 4, we're going to see if there's any symmetry. Remember, when we plug in negative x, we get that even if no signs change, right? And just a quick hint, when do no signs change? When all your powers are even, right? All powers are even, then none of the signs change, okay? And if that's the case, so if it's even, if all powers are even, no signs change or whatever, remember that's x-axis symmetry, which means, well, however it looks on the left side of the x-axis, y-axis symmetry. Well, however it looks on the left side, it will look on the right side. The origin symmetry, that is odds. When I plug in the x's, all signs change, right? And when do all signs change? When you have all odd powers. But here's what's the other thing you have to watch for on the odd one. So all odd powers and no constants. Because if you think about it, a constant never changes the sign. So if you have that, you can't have it on an odd one because it'll never change. It's okay on the even ones because we don't want them to change on the even, okay? And that gives you origin symmetry, which is that rotational one, which means like whatever's in the first quadrant will be the same kind of flipped around in the third quadrant. So a little harder to use that graphing. And use the fact that the maximum number of turning points in the graph is n minus 1, where n is the degree of the polynomial function. So if you think about that, a parabola, you have degree of 2, so 2 minus 1 means I have 1 turning point, right? I have 1 bump. And that's kind of one way you can think about it, okay? All right, so we're going to try this 2 times. And then I strongly suggest you practice it in your homework because that's the only way it gets comfortable. Okay. So we're going to use the leading coefficient test to determine the end behavior, find the x-intercepts, decide where they cross or touch or turn, right? We'll make that little chart. Maybe find the y-intercept, determine if it has symmetry, and then find a few other points if we need to see where it's going. I will tell you right now, I definitely want to see the x-intercepts where we can find them. I want to see some bumps, but sometimes I'm okay if it doesn't hit as high as it should or whatever. I'm not super picky on those where the turns come, okay? All right, so on this first one, very first thing I need to do is put it from highest to lowest power. Negative x to the 5th minus x third plus 6x, okay? You got to keep the signs in front of the terms, So first thing, the leading coefficient test. It's odd, which means they're going to go opposite. And because I have the negative in the front, I'm going to start high and end low, okay? Opposite what it normally starts. So for B, what are my x-intercepts? Well, let's see. First thing I'm going to do is factor out maybe an x, because they all have it. Maybe I'll even factor out a negative x to make it a little prettier. I get x to the 4th plus x squared plus 6 minus 6. Do I have any factors of 6 that subtract to make 1? Yeah, 3 and 2. So I can go x squared instead of my normal x, right? 3 and 2, that's a plus 3 minus 2. Let's see. I don't think that factors anymore, so I think we're good. So when I go to find my x-intercepts, my first one is 0. I'm going to just make a quick little chart. Zeros, multiplicity, behavior. Okay, so my first one, that negative x out front, that's a 0. Shows up once, which means it's going to cross at that. All right, second one here. What would make x squared plus 3 equal 0? Well, x squared would equal a negative 3. You can't take the square root of that. It's not going to be real, so it's not going to cross there at all. It's not even, it's a non-real 0, if that makes sense, okay? So it's not going to show up in the graph. This next one, x squared minus 2 equals 0, so x squared equals 2. Take the square root, we get plus or minus the square root of 2, okay? So the square root of 2 is a 0, the negative square root of 2 is a 0. We need both of those, okay? And they each are the answer one time, so they're going to cross at both of those. And I'm going to just remind us that we can't take the square root of that, right? So you can't. All right, so at 0, I want to cross once. At radical 2, which is like 1.4-ish, okay, I'm going to cross once. At negative 1.4-ish, I'm going to cross once. Okay. So let's see. I found the x-intercepts. I stated whether they cross or touch the x-axis, turn around at each intercept. Okay, so for C, I want the y-intercept. Y-intercept is if I plug in 0 for x, what do I get? And it looks like if I plug in 0 for x, I get 0. So that makes sense. I already can see I'm crossing right there, right? All right, D. Is there any symmetry here? It looks like everything is all odd powers, which means that if I plug in negative, I'm going to get all my signs to change, and I have an odd function, right? So it's probably going to be one of those that I could flip around in that I see that odd symmetry, okay? So it's going to have symmetry about the origin. All right, and we'll see if we need any points. So end behavior, I'm going to start up, I'm going to come through, I'm going to cross over, and I'm going to come back here and cross over and go here, okay? Similar symmetric behavior, I could flip that around, right? The key thing is I started up, I crossed over in my 3 points because I was needed to cross over at each one, and I hit my key points. Now, I could, if you wanted to, run the numbers for that so I knew how far to go down or how far to go up over here. I'm going to be honest, I'm not picky about that. I just want to see those turns, that it makes sure that you go up and down again, okay? And if you think about it, this x squared equals -3, that's going to give me a behavior where I get answers in the i's, right? So somewhere in the middle, that's why those didn't. So we don't see all those turns for a 5th degree, but that's okay, okay, because of that root that wasn't the same. All right, let's try the next one here. Oh, how nice, they factored it for us. That's going to be nice. Okay, we need to find out, though, the degree, because that is going to definitely be a factor here. This has power 3, this has power 2, this has power 1. So altogether, that's 6 degree, which means it is an even function. Okay, so my end behaviors are going to match. They're both going to do the same thing. Because I see this negative here, it means they're both going to start and end down, okay? So that makes that one a little bit easier. For my B, for my X-intercepts, this is, I can go straight to my chart because it's pretty much set up for me. So 0, you know what, I'm going to move this over here because there's more room. So I'm going to put the 0, can't even read this, my multiplicity, and my behavior. Okay, so the first one is a 0 because that -3x cubed, that's 0. There's a multiplicity of 3, which means it's going to cross. I'm running out of room. The next one is x equals 1, because 1 will make that equal 0. It's multiplicity 2, which means it's going to touch and turn. Hopefully you remember what those t and t means. The last one is -3. It has multiplicity of 1, so it's going to cross. It looks like I can't spell cross. Okay. So it's 0, at 1, and at -3. Okay. So let's see, y-intercept. If I plug in 0, well, as soon as I plug in 0 there, everything's going to multiply and get 0, so I get a 0 again, which makes sense because I'm already touching there. Okay. For D, is there symmetry? I could multiply that all the way out if I wanted to. If you think about it, I'll kind of walk through here. This -x will switch power. This one will not. This one will. So we have some that'll change, some that won't. So yeah, it's not going to, we're going to be no symmetry on this one. Okay, so I'm starting down, right? I'm starting down, I come up and I cross over. When I get to the 0, I'm going to cross. When I come up to here to the 1, I'm going to turn and come back down, though. Okay, I'm not going to cross over at that 1, because the 1 is a touch and a turn, okay? And you can see I started low and I end low as well. All right, try them. I'm looking for important parts are end behavior, where they cross, and things that touch and turn and cross in the appropriate places, okay? Intercepts, end behavior, and crossing and turning at the appropriate times. All right, good luck, practice, let me know what you think.